All right, good evening. Welcome back. I just sent a message saying that this evening is not so difficult. I hope you will share this feeling. Hope so. Okay, let me remind you what we did last time. We are discussing functions which are equal almost everywhere. So I gave this definition: two functions are equal almost everywhere if the set of points where they are not equal is of measure 0. This is the definition. And then remember, oh yes, I put it in yellow. Remember, for the notion of Lebesgue measurability for a function, I'm not assuming that it's bounded. So we can define a function which is Lebesgue measurable even if it is not bounded. So if function is Lebesgue measurable and f is equal to g almost everywhere, it means they are very similar, then g is also Lebesgue measurable. This is useful. So two functions can be different than just on a set of measure 0. If one is Lebesgue measurable, the other one is also Lebesgue measurable. And I just introduced this notion of lim sup and lim inf last week. It will play a role next week. So whenever you have a family of functions which are bounded pointwise, which means for any x, when you take all j, it's the bounded set. So for any x, but it doesn't mean it's the same bound for any x, for all x. Then we can define this lim sup and lim inf I explained last week. And whenever you have a bounded set like this, these two functions exist. And it turns out that if all fj are Lebesgue measurable, then the lim sup and lim inf are also Lebesgue measurable. This is important. Then the next thing we did, we took a partition which is Lebesgue measurable, which means it's a partition, but the different set can overlap as long as the overlap is of measure 0. And we have defined for bounded function, which means upper Lebesgue, oh, I did a mistake. Upper Lebesgue sum and upper and lower Riemann sum. No, Lebesgue. So upper Lebesgue sum. The only difference is that I take a partition which is Lebesgue measurable, which is more general than the one considered for Riemann integral. So we can define these two quantities. And we say that the function is Lebesgue integrable if the sup over all partitions which are Lebesgue measurable of this lower sum is equal to the infimum over all Lebesgue measurable partitions of the upper sum. So it's like Riemann, but we have more partitions available. So it means we can easily check that Riemann integrable functions are automatically Lebesgue integrable, but we have more. Now, there is a statement about bounded function. Be careful for this statement. It's only true for bounded functions. If a function is bounded, then the notion of Lebesgue measurability and Lebesgue integrability is the same. It's an equivalence. So it was meaningful to start with Lebesgue measurable function and end up with Lebesgue integrable, but at the end it's the same. Now, if f is bounded on 0 almost everywhere, we can take its Lebesgue integral. It turns out that this is 0. And by the way, yes, I didn't mention, when these two quantities are equal, we just denote them like this. Now, if two functions are bounded on equal almost everywhere, the two integrals are also equal. This is it's a direct consequence of the previous slide. And then we discuss what happens for unbounded functions. And for unbounded function, I started by considering positive one, and I gave a definition of what means Lebesgue integrable for unbounded function when they are positive. And then if there is arbitrary sign, I define f plus and f minus. This is a positive part of f. This is a negative part of f. And if both, now these two functions are positive, if both are Lebesgue integrable in this general sense, then we say that f is Lebesgue integrable, and this difference is the integral on AB f of x dx. So we gave a precise definition of what means Lebesgue integrable for a function which is not bounded and can take arbitrary sign. So it means we denote now by this curly L of AB the set of all Lebesgue integrable functions, no matter if they are bounded. So this is what we did up to now, no matter if they are bounded or unbounded, as long as we use the definition recalled here. This is called the set of Lebesgue integrable functions. Okay. I just want to remind you, if you haven't written any report yet, it's a very good timing to think about it. All right. Okay, so this was for bounded functions. Now we have extended to unbounded one. And I need to just to say that what we have seen for bounded also hold for unbounded functions. So let me just write one sentence about this. All properties shown for what I mean by L infinity of AB intersection with L of AB. This is the set of bounded functions which are Lebesgue integrable. And this is what I have defined up to here. So in particular, this property, so this all properties shown for this extend to L of AB without taking the intersection with bounded functions. So it means what we have, this kind of statement is true even if F and G are not bounded, as long as they are Lebesgue integrable. So this is the meaning of this sentence. And I encourage you to do one or two exercises. I don't write them here, but there are one or two exercises about the notion of Lebesgue integrability with a difference with Riemann integrability. And if you do it carefully, you will see the difference in the process of computing a Riemann integral or a Lebesgue integral. Because remember, when we do a Riemann integral, we do a partition like this. I just summarize it like this. When we do a Lebesgue integral, we do a partition like this. So if you take a function, very simple function, you can do the two process, but you will see when you do it, at the end, when you take a limit, you end up with the same thing. But when you write the Riemann sums or the Lebesgue sums, it's not the same. Okay, so it's quite interesting. And be careful about one thing. There is no contradiction. For bounded functions, these two notions are the same, Lebesgue measurability or Lebesgue integrability. But if F is not bounded, F Lebesgue measurable does not imply automatically F Lebesgue integrable. And there is an easy example. Take the function example. I mean, not automatically. Sometimes it's true, but not automatically. For example, take F in, no, take, let me write it here. Take the function 1 over x on the half line. Or not on the half line, on an interval. Example, take F from 0 to 1 up to R. F of x is going to be 1 over x if x is in the open interval 0, 1, and it's 0 if x is equal to 0. This function like this up to 1 and 1 point here is defined on a closed interval. It's real. You can check this F. F is Lebesgue measurable, it's quite easy to see. You take the fix any s, take the set of x where the function takes a value bigger than s, and you will see that you just get an open interval. So it's Lebesgue measurable, but of course f is not Lebesgue integrable. Otherwise, and you can do it really by checking what means Lebesgue integrable, but if it were integrable, it would mean that this surface is finite, and we know it's not. So for unbounded functions, be careful, you don't have this equivalence. On the other hand, Lebesgue integrable implies Lebesgue measurable, because in the definition of Lebesgue integrable, we have this notion of Lebesgue measurable. All right? Okay. So we know what means now this set of Lebesgue integrable functions. Let me just state one comparison statement, and then we are going to move then we are going to deal with something different from intervals. This is just a comparison. It's quite natural. Let G be a Lebesgue integrable. I'm not assuming anymore that it is bounded. And let F be Lebesgue measurable with f of x, with measurable on AB, also on AB. Otherwise, it's difficult. But with f of x in absolute value smaller or equal to g of x, wait a second, for almost every x belonging to AB. Yes? You forgot your absolute value. No, I can take G positive. Then this simply this assumption is meaningless. In a sense, indeed, if this is true, it implies that G is bigger or equal to 0 almost everywhere. I agree. But I don't need to impose it from the beginning. It's a consequence of this. So let's check. If we know that we can integrate G, we just know that f is Lebesgue measurable. So it's a nice function, but it's a weaker requirement, but it's dominated by this. So it implies that f is Lebesgue integrable. Oh, I can write it. Then it implies that f is also in L of E. So what kind of picture you should keep in mind here? It's quite natural. The picture you should keep in mind is this one. You have an interval, AB. You know that G, it can have a singularity, but still, this is G. You know that the integral on AB, G of x, dx is finite. And f, let me just make the symmetric just. Okay. F is any function like this. This is f. Because it's bounded by G when you take the. My picture is misleading, but it is. Yeah. Okay, if you take exactly the symmetric, it's fine. Just think about it. Sorry, the picture is not. Now it is. Okay. So if f is bounded by G when you take f in absolute value, then you know that f is also integrable. Okay, this is quite natural, even though it can be worse than this, because I could have f also diverging here and also diverging here. if you do it very quickly. So it's not so clear that this function is Lebesgue integrable, but still it is. So, and this notion of a function dominating another one will come back in what I'm going to present later. The dominated convergence theorem. So if you know that a function is integrable and one is smaller, even in absolute value, it's also integrable. All right. Now, so far we have always defined a function on an interval, but what about more general? What about more general domain? What about f defined on omega? More general. No, just an interval. I want something slightly more general. So it's quite natural. If omega is inside an interval AB and omega Lebesgue measurable, remember we have defined this notion of good set. It means omega is not too nasty, but still, I told you, trying to construct an example of a set which is not Lebesgue measurable is quite difficult. So take any set, you have AB, take a set which can be rather complicated. But still it's Lebesgue measurable. I want to define then what is the integral of, sorry, I should say who is f now. Take f belonging to L of AB. How can I define the integral of f on this set omega? Simpler solution. How can I define this? Yes, just define it as the integral of f times the characteristic function x dx on AB. Why it works? Because f is Lebesgue integrable, so it's Lebesgue measurable. This set is also a nice set, and we have seen that the product of two Lebesgue, the set of one Lebesgue integrable function and one bounded Lebesgue integrable function is again Lebesgue integrable. So we can define this like this, no problem. So I don't need to restrict the integral on just an interval. As long as this omega is a good set, I can define it like this. This is quite simple. Now there is one more thing I haven't done. So we treated unbounded functions. On an interval, we treated functions like this. But what about if I move this to infinity? So if I want to define on an unbounded domain, I haven't done it yet. And in the Riemann, this is called improper, thank you. Improper Riemann integrals. I need to define something similar. So my aim is to extend the integral on a domain which is not bounded. Of course, if you have any question, you can always interrupt me. So extension to unbounded domain. So for example, either A infinity or minus infinity B, or even the entire line. How do we do it? So let's start with the first. If f from A to infinity to consider, I should just write, consider So let's assume that the function is well defined. And first I will consider f positive, f bigger or equal to 0 at the beginning, almost everywhere. It can be different from 0 on a set of measure 0. Then we can consider, and I will use the same idea. Let's consider f times this characteristic function on an interval. I recall this is a notion of characteristic function. It's 1 inside AB and 0 elsewhere. Then this is a function defined on AB. Then for B bigger than A. So I'm going to consider this. And now it's quite natural. Again, I want to define an integral on an infinite interval. So if f times this characteristic function belongs to the set of Lebesgue integrable function, it can be a function which is unbounded, but it should be integrable. And so I can take the integral AB f chi, no, let's forget now. Observe that this integral is nothing but the integral of this product. Right. This is quite clear. This integral is the integral of this product because the function is 0 outside of this interval. So because I'm just assuming that this is Lebesgue integrable, so it means this is finite, or it's well defined. And now I take the limit when b goes to infinity. And if this limit exists, it's a limit of numbers, please. This is just a number. It's in fact a positive number because f is positive. So this is a positive number. If this limit exists, then we say, or we write f belongs to L of A infinity. That's quite natural. But this is for positive function. What about function with no specific sign? You define the positive part and the negative part. And you ask it twice. So for arbitrary f from A infinity to R, we consider, so I'm not assuming it's positive, we consider f is equal to f plus minus f minus. I defined the positive part and the negative part last week. Or you just take where the function is positive or where the function is negative, and otherwise you put 0. And I recall that now this function is bigger or equal to 0. This one is also bigger or equal to 0. So I can use my definition. But strictly bigger means bigger or equal. You don't lose anything by writing also the 0.
That's right.
Okay. So for arbitrary f, I consider this decomposition, and if now f plus and f minus are inside this set of Lebesgue integrable functions, even if it is on infinite domain. So if f plus and f minus respect this condition, yes, you can show. Then f is also, this is by definition with the integral of f from A up to infinity. And the only definition I can give is to take the integral of the positive part minus the integral of the negative part. I mean, everything is quite natural. You take the positive and the negative part. If both are integrable in the sense given there, so it means this is a finite number. This one is also a finite number. I can take just the difference, and everything is well defined. Yes?
What about, let's say, you take the function sine of x per x? In that case,
Wait, I know what you want. Let's go step by step. I know why you asked this question, because you did a report on this. Yeah, by the way, it's a good source of information to look at the website. Now it contains many reports which are quite interesting, and the one of that Vic has in mind. I will come to it in a second. Is it clear, this definition? You can also, yeah, that's it. Now, be careful, and this is an exercise. Big, don't say anything. Find a function which is improper Riemann integrable. So you need to know exactly what it is, but not, I should say a function on, let's say, 0 infinity. So a function on 0 infinity, because I want an unbounded domain. Find a function on 0 infinity which is improper Riemann integrable, but not Lebesgue integrable. So it means not, this is not in this L of 0 infinity. So it's a little bit strange, because I said that there exists more Lebesgue integrable function than Riemann integrable function, but now I'm saying something exactly the converse. I'm saying that there exists a function, or more than one. There exist functions which are improper Riemann integrable, but not Lebesgue integrable. So how you should think about it? No, it's a rather complicated picture. I don't know if I can do it. This set is belonging to, oh, it's simply the set L of A infinity. This set is improper Riemann integrals on 0 infinity. So you have many in the intersection, but you have also some functions which are either only in L of AB, L of 0 infinity. And this exercise is about an example of a function which is here. I don't know an example here, but you can probably also find one.
so the Dirac delta function.
No, Dirac delta function is not L.
How about the function is 1 on the.
Ah, yeah, good. You, excellent. Excellent. Thank you. +1. Take H from 0 infinity to R. H of X is 1 if X belongs to Q intersection 0 infinity, and 0 if X does not belong to Q intersection 0 infinity. Because I don't want to have the negative part. I define it on 0 infinity. such a function is here indeed. So we have an example. Good. So indeed, there exist functions which are here, functions which are here, and many functions which are in the intersection. Okay.
Remember you drew a picture where all Riemanns are inside.
Sorry?
You said that all Riemann integral functions are Lebesgue integral.
Bounded. And it was, be careful, it was on bounded interval, it was on AB. I do an extension now. You're right. So we should not be confused. Oh, sorry. Okay, you add what is missing. Q intersection 0 infinity. You should not do. You should not be confused with this picture. This is Riemann int on AB, and this is L of AB intersection bounded. Sorry, I should take Riemann integrable and bounded. Unbounded. I took it bounded as on this L infinity intersection with, yes, L infinity of AB. There is no contradiction between these two pictures. This is for an interval, and I'm considering bounded function. All Riemann integrable functions are Lebesgue integrable. That's it. But now, please be aware, this is an extension on a half-line. So you cannot apply this statement directly, and it turns out that on the half-line, that's it. That's life. I don't want to, it's no more written. So you can do similar. I can do a similar construction for L of minus infinity B. You can just copy and paste, but you take a limit to minus infinity.
I mean that function is not Lebesgue integrable.
No, this one.
If it's bounded.
No, this one is bounded because it takes only the value 0, 1, so it's a bounded function. The problem is I consider it on 0 infinity. In fact, this function is also, if I restrict it to an interval, it's already here. So here I restrict it on the interval 0 infinity, 0, 1, or any bounded interval. Here I'm considering it on 0 infinity. That's it. You can do the same thing for minus infinity to B and for L of R, but be careful. L of R, you first take a limit to minus infinity and then a limit to plus infinity. So it means you take limit A to minus infinity, B to plus infinity separately. Don't do it. So you first consider limit when one boundary is going to plus infinity and then the other boundary going to minus infinity. Don't take these two limits simultaneously going to plus and minus infinity because you might get something annoying. There are counter examples. But okay, this is quite simple. Do you have any question or remark? Everything is clear. Ladies, is everything clear? Yes, both of you. Can you follow? I know it's hard, but if you understand 25%, and if you get some pictures like this, or keep in mind some functions, this is already good. And discuss with your tutor, this is part of the job. Yeah, I know it's hard. Your first year, first semester, I mean, nobody is doing this. Except you. Yeah. No, precisely in calculus 1, I warn you, I wanted you to be careful about taking the limits together to plus and minus infinity. This is dangerous because you end up with some, not contradiction, but with some results which are very annoying. So the definition of what is or for Riemann, but here we discuss Lebesgue. What means Lebesgue integrable on R? You first define, so take a f, define on the line. Then you integrate from A to B, f of x dx. So you need to assume that this is finite. Then you take limit when A goes to minus infinity. Assume that this is finite. And if it is finite, take the limit when B goes to plus infinity. And if this is finite, then you say that it's Lebesgue integrable on the entire line. Yes, sometimes, but this is a different topic.
He's talking about the symmetric function.
Yes, you're right. Sometimes it's useful, but it's a slightly different framework. You know, like Dirac delta function, when you speak about calculus 1, you don't speak about Dirac delta function because it's not a function. You need to go in a larger framework, and then you can speak about Dirac delta function. The definition of Lebesgue integrability goes like this. Now, I'm not saying that you cannot take the two limits together, but it's in a slightly different framework because you have to be careful not to get something meaningless. Okay. Any other question or remark? So now I'm going to introduce a very useful result which has already been used in some reports, and probably you can use it for your major, whatever it is. Even in economics, you can probably use it. This is called the dominated convergence theorem. In fact, I'm pretty sure that you have used it without knowing this theorem, because you have done some computations which were not justified, but we are going to justify them. So you should think about this exchange of a limit and an integral. You know, these are too complicated procedure, an integral, a limit. Sometimes you can exchange them, but not always. Okay. So what is a framework? First, I need to define what is a pointwise convergence. So we consider a set in R, arbitrary set. And a family or a sequence Fj of functions with Fj arbitrary functions from omega to R. So just a family of functions. But now I'm going to assume that it is pointwise convergent. We have already seen pointwise bounded. I explained it again at the beginning. Now I say this sequence is pointwise convergent is pointwise convergent if limit when j goes to infinity, f of j is equal to f of x. What does it mean? If I write it's equal to f of x, it means it exists. Meaning it exists when we call the limit and we call . f of x. But I don't need this to exist for all x, for x almost everywhere. So for almost every x belonging to this omega. So it means if it is not true for a set of x which is of measure 0, I don't care. You just need it for x on a set, or it's you can x of, oh sorry, I have to put a x here. Sorry. You take a x, you compute fj of x, and this limit has to exist almost everywhere. Okay? So for almost every x. This is a notion of pointwise convergence. Pointwise means you do it at every x, or almost every x. And if you remember the notion of limit, it implies that for any epsilon bigger than 0, there exists an n. This is a notion of limit. There exists an n natural number such that the difference between fj of x and f of x is smaller than epsilon for all j bigger than n, right? This is the notion of this limit. What is the point? This n depends on, of course, epsilon, but it can also depend on x. So for different x, the capital N can be different.
Is it allowed to depend on the function?
Of course, for sure, it depends on the function. No, for sure. So it depends on epsilon and on x. Yeah, if you take a different function, you will get a different n, sure. So this is this notion of pointwise convergence. Let me just give you an example or two examples of pointwise convergence. Set fj of x is x power j for x in the interval 0, 1. What is a pointwise limit? Can you tell me what is the limit when j goes to infinity of fj of x?
0, except when x is 1.
Yes, it is 0 if x is in the open interval on the right, interval 0, 1. But if x is 1, it's 1. Because 1 power anything is still 1. So you have, and observe, this is a very nice function, just a polynomial. Nevertheless, its pointwise convergence is to this function, which is 0 and 1, which is not at all continuous. Another example, set fj of x is j. Again, I take 0, 1, and I consider this function. Think about this function. It takes a value which is bigger and bigger, but on an interval which is smaller and smaller.
Is that x not a characteristic function?
Yes, it's a characteristic function on this. So you're right. Okay, let me write it differently. It's equivalent. So it is j if x is inside 0, 1 over j, the same, the characteristic function, and it's 0, 0 otherwise. Okay. Then what is the limit when j goes to infinity of this function?
Just infinite. Can I put limit infinity though? I don't think that that's well defined.
Infinity is not well defined.
Exactly.
Is it infinity? Who can tell me this limit? Pointwise limit.
You're everywhere. You're everywhere. I mean, it's like there's a jump from one of the changes here.
Look at the definition. You fix a x and take j goes to infinity. It's 0 everywhere. It's 0 for any x inside the closed interval 0, 1. Check with a picture. You have a family of functions which are more and more concentrated near 0. So I do a zoom near 0. You have one function which is like this. The next one. The next one is like this. And next one is like this. Okay. So this is one, let's say this is 2, 3, 4. 2, 3, 4. But observe, if you fix a x, no matter where, you fix a x and take j going to infinity, then this function will be on the left of x. And 0 is a little bit special, but from the definition, 0 is 0. That's why I took open interval. If you close the interval here, you have a small problem at 0. Even with this would converge to the Dirac delta function. So this is this notion of pointwise convergence. And if you want to come back to the distribution exercise, but this is something we have already seen Fj converge to delta 0 in the sense of distribution. So more precisely, I should not write Fj. What should I write? This is not very correct. T, the function which is associated, the distribution which is associated with this function. But this is something we have done already 1 month ago.
Oh no, it's delta 0.
Delta, sorry, so delta 0.
I'm sorry.
So we have seen this notion of, I have introduced this notion of pointwise convergence. Now, what is a dominated convergence theorem? And I told you it's an important subject, or it's an important result. But first, do you have any question? Yes. In the definition of pointwise convergence, I think I just need it for almost every x. It's not written almost every x. Okay, so I will correct it. It depends what you do. Sometimes you need it, if sometimes for some requirement you need it everywhere. Sometimes you need it only almost everywhere. So it depends. But yeah, probably we are in the Lebesgue theory, and in Lebesgue theory, you can always forget a set of measures 0. So it's better to write almost everywhere. Okay, I will correct it. What is this dominated convergence theorem? And the title says it's a convergent but dominated. Okay. So I consider a family of functions or a sequence of functions. I should say they're defined in an interval. Are all defined on this interval AB. This value in R. I consider family of functions like this. They are all Lebesgue measurable. Lebesgue. This, you shouldn't be scared by this notion of Lebesgue measurable. All continuous functions are Lebesgue measurable. So it contains really plenty of functions. It's more general measure. It's a very large set of functions. So we consider family of functions which are Lebesgue measurable and such that precisely the limit j goes to infinity, fj of x is f of x almost, or for almost every x in AB. So this notion of pointwise convergence, but almost everywhere. So it means it can be not true on a set of Lebesgue measure 0. Now, suppose, and this is really the big assumption, suppose there exists a function g. For Vic, it's a positive one, but I don't need to assume it because the next condition is going to impose it automatically. So G Lebesgue integrable and such that fj of x smaller or equal to g of x almost every, for almost every x inside AB. And what is the name of this function? You can guess, it's a dominating function. And by the condition, it's a positive function. So the g is called dominating function. Why? Because it dominates all fj. This, usually it's hard to find this function g, depending on the context. And then what is the conclusion? Part of the conclusion we already know. Then fj are Lebesgue measurable. I already mentioned this a while ago. If you have functions which are measurable and dominated by a function, then these functions are integrable. Oh, sorry, Lebesgue integrable. Sorry. Lebesgue integrable. So you can take the integral, but it's only true, not only true for fj, but it's also true for f. Because it's not automatic. But it turned out that because f is a limit of fj and each fj is bounded by this g, then it's also true for f. So these are Lebesgue integrable. And the most important thing is limit when j goes to infinity of the integral AB fj of x dx. Don't tell me that this is trivial, because this is not trivial. I mean, the last equality is trivial because it's by definition. But what is not trivial is this exchange. the fact that you can exchange a limit with an integral. Think about it. It's not trivial because in this integral, if you come back to the definition, it's a complicated process. You have a supremum over all partitions, blah, 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 blah. So you are exchanging a supremum with a limit. So you are taking two complicated operations. But nevertheless, it's true as long as there exists this dominating function. If you don't have this, it's not true. Can you tell me what, can you show me a counterexample where if you don't have this condition, it cannot be true? No. A family of functions where you cannot exchange this. Exactly the example I shown before with this J times characteristic function. If you don't have G, then think about this. So let me write it. If we don't have G, then the Dirac delta distribution would be a function. So remark. If we don't assume the existence of G, we don't assume the existence of G, then delta 0 would be in L infinity, let's say, of -1, 1. Just take an arbitrary interval. It would be a function, but we know it's not a function. You can check it doesn't fit with the definition of a Lebesgue integrable function. Why? Because why? I mean, this statement would be true. Take exactly fj, the one I have defined before. Fj of x is this j if x is in 0, 1 over j, and 0 otherwise. Take this. Observe that you cannot find a g because it's becoming bigger, bigger, and bigger. And your g will not be integrable. So you cannot find a g. So for this kind of function, and it's clear that this equality, check that this equality is not true for this t. What is this integral for this fj? No, it's always 1. What is this integral for this fj? 1 is not equal to 0. But there is no contradiction because this g does not exist. So it means here the assumptions for this family, the assumption about G is not satisfied. So it means I cannot apply this theorem. And it's clear that I cannot apply this theorem, otherwise you would have 1 is equal to 0. What? No, this I computed before, and somebody said the answer this for this example here, this is always 0. So the integral of 0 is 0. Here the integral is always 1. So if we were able to, if this equality would be true, then we would have 1 is equal to 0. But this equality is not true in general, except if you have this dominating function, and we don't have it in this example. So you can see this is really necessary. I'm glad that we have this example, or counterexample. Sorry? No, it's a counterexample that you cannot exchange these two if you don't have the dominating function.
Okay. I thought you said something about theorem, which I think doesn't this.
No, it's a counterexample of this equality in general. In general, you cannot prove this is not true, and we found a counterexample. As I said, this is a theorem. Probably, if you are not very careful, you have already used it. Yes, but precisely I said that there is a small gap. But now you understand what is a gap, and you can check that in calculus we had this dominating function. So I could do it. So in calculus, you will probably do something like this, and your teacher should tell you, oh, you can do it, but he will not mention all this. But in the example where he's using it, there exists such a G. All right. That's all for this dominating function, the dominating function theorem, dominated function theorem. Again, you need to satisfy these assumptions. All right, next. I guess we will more or less finish this chapter next week and then move to the last part of this course. Hope so. No, it's okay. I don't know. Also, maybe we'll not finish next week, but the week after. But yeah, the last topic, we can speak about it for one semester if necessary. It's a very large topic. But 2.6 LP spaces. LP spaces, and you should. There are two very important ones, L1 and L2, and L infinity. But I will give the definition of all LP, but the one for you which are really useful are L1, and L1, I already mentioned it. I mentioned L1 lock, and I said we are going to come back to this during this chapter. Okay, but I want to extend what we have done. So now I'm going more or less to do some blah, blah for 15 minutes. Sorry. So Lebesgue integrals. Who is this? Okay. Sorry. Lebesgue integrals have been defined. Remember, I define Lebesgue integral on an interval. While if you come back to Lebesgue measurability, it was in Rn. I hope I don't say something wrong, but yeah, Lebesgue measure was introduced on Rn. But Lebesgue measure was introduced on Rn, which means, and you can, of course, it's not completely straightforward, but you can check rather easily that everything we did on AB, we can do it on a subset of Rn. So it means we can define L of omega for good subsets of R. And what do I mean by good?
LM.
Sorry?
LM. LM is in the Lebesgue measure.
Yeah. I mean, instead of an interval, I can do it. For example, what means good? For example, I want to go in Rn, so I can, instead of taking an interval, I can take a box. For example, omega is a box. And I have defined a box in Rn. It's a box. This is a box. Just do it in n dimension. Okay. So instead of an interval, you look at the definition and you replace the interval by a box. You can easily define the notion of Lebesgue measurable function and Lebesgue integrable, or omega an open set. A box open and bounded set in Rn. The theory works very well. I didn't probably I should have done it from the very beginning in this framework, but I think it was already complicated enough. But if you look at the definition, you can really replace this interval AB by a box or open set in R. So I will use this notion of good subset in the sequel because it's natural. So I will define functions on a set omega in R. So from now on, I will not stick to the one-dimensional case because it's not sufficient in many applications. From now, we consider L or F belonging to L of omega for omega inside Rn. Either open unbounded or close unbounded. These are the two situations which are really interesting. Think about a box or open board or something like this, and you can check everything fits nicely. But there is one result which is new in n dimension. So all the results I have presented are possible on this. You can really go, it's straightforward. But there is one new result, which we have already used in Calculus 1 without justifying it. So now I give you the precise statement. It's called Fubini's theorem. So one result, yes, one result specific to Rn, for n strictly bigger than 1 in R1, it doesn't say anything because you have only one variable. I want to exchange the variables. And I don't state it in full generality, I do it in 2 dimensions. That's enough, if you understand it, in 2 dimensions. So this is called Fubini theorem. And you will see the statement is not completely trivial. So we consider I, which is a box, I1 times I2. So if you do a picture, you have I1, one variable, this is I1, you have I2 here. So what is the product of I1 times I2? It's not the area, it is this surface, this is R. It's a notation for this box in R2. Okay. And so this is a subset of R2, but it's a very specific subset, it's a box. That's it. And consider F Lebesgue integrable on I. So I haven't defined it exactly, but this is exactly what I mentioned as an extension. It means you look at the definition of Lebesgue measurable. First, you start with bounded functions. You take the notion of function which is Lebesgue measurable, and then Lebesgue integrable. It's really the only difference is when you do a partition here, you are going to consider a partition in 2 dimensions instead of 1 dimension. And so you are using the Lebesgue measure of these sets when you define the integral. That's the only difference. So I consider a function which is Lebesgue integrable of 2 variables. Now, what is a statement? It's a long statement. It's in 3 points. Now, almost every x belonging to I1 function so looks I fix a x and I look at this function of 1 variable. And the statement is for almost every x, this function of 1 variable is Lebesgue measurable, unintegrable. Can you tell me why I put both? Should be, wait a second.
I'm so sorry.
Why I have to write both? Why I need to write both measurable and integrable? I have not assumed that f is bounded. I have just assumed that it is integrable. So it's, if it is not bounded, these 2 notions are not equivalent. So I need to say that it's measurable, and then it's one more condition that it is integrable, because it doesn't imply it. So it says that when you fix x, this function is Lebesgue integrable, measurable, unintegrable, and we write integral on y2 f of x y dy for its integral. And the claim is that this is a number, a well-defined number, for almost every x. What is the second? But look, this number, it depends on x. So now the second statement is the function. Now take x in y1 goes to this number. This number depends on x, so I can consider it as a function of x. This number, or this function, is Lebesgue measurable on I1 and integrable. And I'm going to write what is its integral, or the notation for its integral. With integral. Integral on y1 of the function integral on y2 f of x y dy dx. So the order is very important because it is in the way I define it. On the third statement, one has this guy. So this guy, which is integral on I1 of the integral f of x, y, dy, dx. this guy is equal to the integral f of x, y, dx, dy, written like this. So what is this notation? I assume that this function is Lebesgue integrable as a function in two variables. So this is the limit of this process with two variables as a function of two variables. And now I started with the first one, and then, I started with the second variable and then the first variable, but of course I could exchange. So it turns out that this is also equal to the integral now starting on I2 of the integral on I1, f of x, y, dx, and then dy. And now you have the full statement of what we use in calculus 1. Of course, no, it was calculus 2, right? It's two variables or n variables. It said that for any function where this integral is meaningful, and in particular, no, that's it. For any function such that this is meaningful, you can take really in any order, but the meaning is very precise. I'm not saying that this integral exists for all x. It exists for almost every x, but this is sufficient because function can be changed on a set of measure 0, so you don't care about a set of measure 0, and then you have the second one. And this is Frobenius, which simply does not exist in one dimension. Right? So I wanted to state it because it's natural in this framework, and because, as I said in calculus 1, we are using this equality many times. Okay, so this is a first extension from one variable to n variables, but if we have n variables, we need this Frobenius. Second extension, and then I stop doing blah, blah, blah. So far, we really discuss only real valued functions. So we have, it's a new remark. So far, we consider, in this chapter, we consider f, let's say from omega, but to r. Everything was real. For LP spaces, if you have never seen complex number, keep it here, real. But for what I'm going to say, there is no problem of considering complex valued functions. So let's just go to more general framework. Now we consider f from omega to k, which means, I just remind you, this is R or C. So if you don't like C, you can always think about R. If you prefer complex functions, you can take with C instead of R. But observe that if f is from omega to C, one has f of f, I can always write it as its real part plus its imaginary part, f plus f bar. So if you have never seen complex numbers, just forget these few minutes, because I cannot explain what means this bar. This bar has nothing to do with the bar used for closure. This bar is for complex conjugate. complex conjugate. And what we observe, this function, oh, there is a mistake. To divide by do I. This function is real. Yes. But look, if they don't cancel, it wouldn't be equal to f, because if they cancel, you have f over 2 plus f over 2. It makes f. You have f bar over 2 minus f bar over 2. But why I do it like this? Because this is real valued. It's real. And this one is also real. So it means f can be written as a real function plus I times a real function. So these two functions are real. Okay. So it means any complex valued function is just the sum of two real valued functions. No, I mean, this is a proof.
Two real valued functions is the sum of one real value and another one times I.
Yeah, sum with the coefficients in C.
Okay.
A sum of a real valued function plus a I like in Vic. There is an I in Vic, I times a real valued function. Okay. Yes, Vic is complex, you're right. That's true. Okay, please let me finish. So it means f can also be written as real part of f plus I times imaginary part of f. And what is this? This guy here is this one here, and a second color. This guy here is this guy here. Okay. So it means then if and I'm going to give a shorter name because this is too long. I'm just going to keep this FR for real and FI for imaginary. Then if FI and FR are in L of AB, we say that F is in L of AB. There is a small trick in this sentence. Oh, no, I should say omega. I'm slightly more general. And of omega, then what is the meaning? It's a little bit confusing. The first line, you should understand it, because these two functions are real valued. So this is what we have done until now. I'm just saying two real valued functions are Lebesgue integrable on omega. If they are Lebesgue integrable as real function, then this is a new definition. I'm saying that this function, which is complex valued, the f I'm considering is complex valued, I put it in the same set. The only difference, maybe now I can write, I should write, but I'm not going to do it, with value in C instead of with value in R. I consider function from omega to C instead of omega to R. But I keep the same notation. It's natural. And what is integral? What is integral on omega of f of capital X dx? Because it's a sum of one real function plus I times a real valued function. This is by definition integral of f real part of X dx on omega plus I times integral on omega of f of X, imaginary part dx. So nothing very surprising. All right. Okay. So far, so good. And now let's have fun. I need one more definition. Oh, it's not really a definition. Remember, my aim is to define LP. I did not mention so far who is this guy. I'm going to start with L1. What is L1? No, not local. I'm not writing the L1 local. I will come back to it later. So we consider, I want to define this. So we are going to consider what is called the equivalence relation F for, I should say F and G are from omega to Q. Equivalence is equivalence relation for F and G from omega to K. F is equivalent to G if, I need to define it, F is equal to G almost everywhere. So what I'm doing, I want to put together two functions which are equal almost everywhere. I want to put them in the same box. If you don't know what is an equivalence relation exercise, and this is an easy one, it's a 2-line exercise or 3-line exercise, check that this curly is an equivalence, like equivalence relation. So if you don't know what it is, check this exercise. It is in the notes. You will learn what is equivalence relation. It's very simple. And I'm going to finish with this, and I will explain it later, next week. So let me give you the definition of L1. L1 of omega is L of omega. I hope you like this definition. What is this definition? This is the definition. But what is the meaning? It means elements of L1 of omega are made of equivalence classes of Lebesgue integrable functions, equal almost everywhere. So it's probably better to stop now, because if I start to explain more, it will take more than 5 minutes. So I need to explain this, but don't worry, if you don't understand this definition, I will come back to it next week. But I just want to emphasize, I want to put together functions which are equal almost everywhere. And this is quite natural because remember something I already mentioned. Remember this result I mentioned. I will come back. If f is equal to g almost everywhere, then the integral f of x dx, now I can do it in omega. is equal to the integral of g of x dx. So because of this result, I don't want to see the difference between f and g. So as long as they are equal almost everywhere, I put them together. So this is this notion. So I will start again from this next week. Again, if you haven't submitted any report, it's a good time because it's in the middle of the semester now. If you have any question, you can ask me. If you have any question, you can ask to the tutor. Okay, so don't hesitate to contact us. Right? Okay.